Hi everybody. I am homesick today, but I don't want to lose a day in our progress here. We've lost a day already, and the end of the term is coming fast. So I'm going to try to go ahead with the lesson we were going to go through today using this video. Couple things, understand I'm sick, so I may need to take a coughing break, not coffee break, but a coughing break. And then also my computer's kind of messed up, so my tech won't be might not be as clean as usual. So just bear with me and forgive me for any mistakes and coughing I do in the next few minutes. So I want to run through at least one example. I wanted to, I had hoped to go through two today. I'm going to see how long the video goes because long videos aren't a good thing, I have learned. So I'm going to go through at least one today. First, I want to remind you where we're at. We're talking about optimization, the important steps to optimization. Excuse me. Make sure you read your story more than once. As you're reading your story, make sure you identify the value you're looking to optimize and you identify the constraint. There will always be a constraint, and it's important to identify the constraint. Sometimes the constraint can be put in the forms of an equation, and sometimes it can't. If I get to a second example today, it will be an example where you can't put it in the form of an equation, but if I don't get to it, that doesn't stress me because it will be so obvious. I don't think it's going to be a problem. The next step is to combine your constraint and your optimization into one equation. That's because obviously we're going to be taking the derivative. Make sure your equation involves the value you're going to optimize. If you're going to optimize area, you don't want your equation to be about perimeter. Once you've got it into one equation with one input, then consider your domain. If your domain includes endpoints, then you can continue like we did last week. You can use the extreme value technique that we've used, test your endpoints, and do all that. If you don't have endpoints in your domain, then that's the kind of thing we're going to talk about now. So once you've considered your domain and the endpoint, like I said, the endpoints are really important in your domain, then find the extrema using the techniques that we've been learning. Take the derivative, find your critical points, etc., etc. Then you verify the optimization. That's when endpoints come into play. And like I said, we're going to talk about that later. And then finally, make sure you answer the question. If the question is find the dimensions, find the dimensions. If the question is find the area, find the area. Make sure you've answered the questions or you give me no choice but to start taking off points. So here's the question we're going to talk about, or the first problem, or maybe the only problem we'll see. We want to make a cylindrical can to hold 1.5 liters of liquid. Find the dimensions that minimize the required material. Little back note here first. I think we began a problem last time we were together, and I said I was going to finish it. Honestly, I don't remember what it was because it's been too long and my brain is fuzzy from being sick. So I don't remember what the problem was. I believe that this problem answers the same issue that problem was going to address. So you can either go back and finish that later, or we can finish that together later. But this is going to deal with the same situation. So okay. So here's what we've got. The first thing, and normally I wouldn't give you a problem like this, but I think it's an interesting thing to consider. If we're going to talk about the dimensions of the material to make a cylinder, notice that this liters unit is really not useful. We're going to end up probably talking in centimeters. I happen to know, and I think it was referred to, it might be referred to in the homework or something, I don't remember, but 1,000 cubic centimeters equals 1 liter. Score 1 for the metric system. So we know that 1.5 liters is the same thing as 1,500 cubic centimeters. So let's just make that modification now. That would be a worthwhile conversion to memorize. So what is so let's talk about what we've got here. We've got, I wish I'd drawn this offline rather than having you watch me. Ugh. Okay, so here's a cylinder. What do we know about a cylinder? It looks like this. We know it has a radius that we'll call r, and it has a height that we'll call h. If you're making a cylindrical can and we want to minimize the material required to make the can, well, we're talking about the surface area of the can, and the surface area includes the sides and the top and the bottom. So we know that area is going to equal the top and the bottom are each pi r squared, the area of circles. So the two of them together is 2 pi r squared. And then the side is going to be a rectangle. If you can imagine, you should remember this from geometry, but in case you don't, if we were to unroll this can, the sides would be a rectangle whose height would be h and whose width would be the circumference of the circle, which we know is 2 pi r. So if the circumference of the circle is 2 pi r and the height of the can is h, that's the surface area of the sides. The beauty of a video is you can always pause and go back and replay. So I'm trying to talk relatively quickly to keep the video from getting too long, but I know that you have the power to pause and back up and replay. So I feel okay about the speed with which I'm talking. So this is the thing we intend to optimize. In fact, you know what? I wish instead I'd wrote minimize. Oh, I deleted too much. Let's see. Yep. So this is the thing we're going to minimize. What is our constraint? I wish I'd written this on the left instead of the right, but I didn't. So there we go. Our constraint is that 1,500 cubic centimeters must be the volume of this can, and we know the volume of a can is the area of the top multiplied by the height. So that's 1,500 equals pi r squared h. So just like we did before, we're going to take our constraint, solve for one variable, and plug that into our optimization equation. With a couple minutes of thought, we see that it's going to be a whole lot easier to solve for h, and also there's only one occurrence of h in our optimization equation, so clearly that's the way to go. So this equation becomes h equals 1,500 divided by pi r squared. So I'm going to take 1,500 divided by pi r squared, and I'm going to plug it in for h. All right, everybody feeling okay? I hope so. Hold on, I'm changing my mind here. Let me make sure that what I'm about to write matches that. Okay, I'm going to try something. I may be crazy, but I'm going to try it anyway. I'm going to take this and try to copy it to a new page. Oh, it's magic. Tech is amazing, isn't it? Okay, so now the question is, can I get back to my pen? Yes. Okay, so what I'm going to do now is I'm going to rewrite this top equation. Oh, let's go all out, and I think I'm going to erase the h, and in its place I'm going to write 1,500 over pi r squared. All right, everybody good with that? And I'm going to delete this thing. Hopefully this works. No, it doesn't. Oh, darn. I had high hopes, but there, I'm just going to move it off screen. Okay, so there we are. So we've got this as our equation. I'm sorry, my computer, like I said, is a mess. Okay, that'll work. So this is the equation we have. Let's clean it up a little bit. So area equals 2 pi r squared plus this 2 times the 1,500. Okay, sorry. Here's where the foggy brain kicks in. The pi's cancel. This r cancels with one of these r's, and we're left with 2 times 1500 is 3000 over r. So let me check my notes and make sure. Yep, that agrees. So if we're going to take the derivative, I'm going to rewrite this like this because it's going to make taking the derivative a whole lot easier. And we get that a prime equals, okay, not yet. I'm sorry, I'm jumping ahead. So we now have a as a function of r, which was one of our goals. I'm going to rewrite it neatly. A of r equals 2 pi r squared plus 3000 r to the negative 1. It's time to think about our domain. This is where we're similar to the last example. We know r is basically, well, r can't ever be 0, right? Because if it's 0, then we can't meet the volume requirement. But as the radius gets infinitesimally small, the height must get infinitesimally large. So we really don't have boundaries on our r. And for that reason, while it seems like a silly thing to waste time thinking about, for that reason, our extreme value technique fails us. Just because we find a critical point, we can't be assured that it is the extrema, because we have to worry about our asymptotic endpoints. Whatever crazy thing is going on, we have to worry about it. So put that in the back of your mind and realize when we get to the verification stage, we're going to have to worry about that. All right, I'm going to move to a clean page. So we have that I as a function of r equals 2 pi r squared plus 3000 over r, 3000 r to the negative 1. So what is a prime? Because we're still all about finding the critical points. A prime is 4 pi r minus 3000 r to the negative 2, which is the same thing as 4 pi r minus 3000 over r squared. So now we got to think about what are our critical points. I'm going to clean this up just one bit more. I'm going to multiply. You're fine, honey. It's going to be a whole lot easier to think about our critical points if we make this into one nice rational function. This becomes 4 pi r cubed minus 3000 all over r squared. Now what are our critical points? We have critical points happening in two places. We have critical points where a prime does not exist, and that's at r equals 0. And we have a critical point of a prime equal to 0 at 4 pi r cubed minus 3000 equals 0. Okay, so we add 3000 to both sides. I'm sorry, this is getting sloppy, but I'm going to do it anyway. 4 pi r cubed equals 3000. We divide both sides by 4 pi. R cubed equals 3000 over 4 pi. Take the cube root of both sides, and we get that 3000 divided by 4 pi. I'm going to grab my calculator because I'm afraid to trust my notes. So I'm checking 3000 divided by 4 divided by pi, and then raise that to the 1/3 power. Oh, good. My notes were right. Turns out R equals 6.2035. If this was a square root, we'd have to worry about the negative, but we'd be able to ignore the negative because we're talking about a radius, and radius can be negative. So, so we get this. At this point, I'm going to pause and take my daughter up to the bus. I will be back. Okay, I'm back. Sorry about that. I had to take a little break there. So let's recap. We found in our attempt to optimize R, or optimize surface, minimize surface area, we found the derivative of area, surface area, which is here on the screen. Remember, our domain is 0 to infinity, not including the endpoints. And then we found the critical points of 0 and 6.2035. The next step you want to do is consider, are your endpoint or your critical points actually in your domain? And no, 0 is not in our domain, so we can't consider that. That gives us only one critical point. We should feel pretty confident it's our answer, but we can't skip the verification step. And we need to make sure, you know, we didn't do something haywire, and instead of minimizing surface area, we've maximized it, which, you know, if you think about the scenario, that's crazy, because a very, very small radius and a very large height would probably be maximizing. But nonetheless, you still need to test it. And because we don't have endpoints in our domain, we can't use the extreme value technique that we know. So instead, we can resort to first and second derivative tests. So what I suggest you do is think about the first derivative test, where we consider 6.2035, and we think about the derivatives on both sides and what that means the slope of the derivatives is doing. Not 5, but 7, of course. And if you plug that into your calculator, you find that a prime of 5 is negative 57 point something, and a prime of 7 is a positive 26 point something. So we know this slope is going down, this slope is going up, and this is in fact our relative minimum. So the last excuse me, the last step is, so our verification is done, and the last step is to go back and actually answer the question. And the question was, find the dimensions that minimize the required material. So we've got that our radius equals 6.2035. We can go back to our initial constraint equation to find the height, and we find that the height equals 12.4070. And that, whoops, that was a messy square, but the problem is done. That's the final answer. So the point of this exercise was really to show you how you can use the first and second derivative. Well, we didn't look at the second, but you can imagine we could have taken the second derivative and used the second derivative test to prove if 6.2035 was a min or a max. So I'm going to stop there. What I want you to do now is try to complete the homework assignment. I don't remember what the number was, but on Ames it's called optimizations. The last one is hard, I'll warn you. We'll go through it together if need be. If you complete, well, let's just leave it at that. Go ahead and finish the optimizations homework. When I'm back tomorrow, I'm sure I'll be back tomorrow, we'll do another kind of example and make sure we get these all squared away. I encourage you to ask your classmates for help. I know together you're all capable of getting this done. So spend the rest of class today working on the rest of the homework. And I'll see you all tomorrow. Bye-bye.